Anyway, so we have this box of 10 kilograms. It's pushed from rest, right, along rough horizontal ground by a horizontal force of size 50 newtons for 3 seconds. The coefficient of friction is 0.45. Find the speed when it stops being pushed. Okay, so it was pushed for 3 seconds. So what's its speed after 3 seconds? Right, in order to calculate speed, right, we're probably going to need to have the acceleration, right, which means we're going to have to resolve these things. So in my diagram here, I've written everything that I know. I have my 50 newtons pushing force. I don't know what the friction is yet. I don't know what the contact force is, and I know what the weight of the object is, right? It's 10 kilograms down. And remember, weight always acts straight vertical. And I've also stated the direction of acceleration and the direction of motion, right? I've set them both in the direction the object is being. Right, from here, it's actually a very simple process, right? You're going to start getting into the habit of doing this with these kinds of problems. Is we're going to resolve vertically to find the normal contact. So if I resolve vertically, right, remember vertically in this example is perpendicular to the direction of motion, which means there's no acceleration. In other words, the forces are in equilibrium. That tells me that my normal contact force must be equal to 100 newtons. Right? So my normal contact force is equal to the weight of the object. There I've resolved vertically. Right, now that I have my normal contact force, the next thing I'm going to do is calculate the friction. Right, the friction is whatever the normal contact is multiplied by the coefficient of friction. So I'm going to go back to my question and see, right, they gave me that as 0.45. So I'm going to have 0.45 multiplied by this 100 over here. And that means the friction force is going to be 45 newtons. Okay. So I have my normal contact force. Now I have my friction force. So the only thing to do now is to calculate the net force. Right, so you can even write on your diagram now that you've calculated this as 45 newtons. So you can see I've got 50 newtons going in one direction and 45 going in the opposite direction. So I can already see that I have a positive 5 newtons force in the direction of motion. So I'm ready to calculate my acceleration, right? This is my net force, right? My net force is in the direction of motion, and this happens to be the 50 and the 45 newtons, right? 50 is going in the direction of motion, so it's positive, and I'm going to add the force going in the opposite direction, right? So I'm going to add minus 45. Remember, direction is important. If it changes direction, it's negative. The mass of the object is 10 kilograms, and I want to find the acceleration. So I'm going to have 5 divided by 10, which I believe gives me 0.5 meters per second squared. So there's my acceleration. Okay. Now I can go back and I can think, what information did I have? So I go to the question and I can see that it was pushed from rest. So I know my initial velocity is 0. I pushed the object for how long? For 3 seconds. How was I pushing it? Well, I was pushing it with an acceleration of 0.5 meters per second squared. And so now I can calculate the distance that this object was pushed in those 3 seconds, all right? So the variable I want to solve for is final velocity. So I can use v equal to u plus at, all right? That'll give it to me in one go. The final velocity is what I'm trying to solve. The initial velocity is 0 plus 0.5 times 3. So 0.5 times by 3 is just 1.5 meters per second. So there I have the final velocity of this object. Cool, everybody happy with that?
Yeah.
Yep.
Nothing funny about that over there. Still got my notes up from like 2 weeks ago. Oops, sorry. There we go. Okay, so that's part 1 done. Now let's have a look at part B. So this is where things are going to change now, right? And so you can imagine if things change, we're going to have to change our diagrams and stuff. So it says the box then slows down because of friction. Because remember, we've stopped applying the pushing force. So we pushed the box, and after 3 seconds, we stopped pushing the box, right? We want to find the total distance the box has moved. The total distance, okay? So now you need to think to yourself, right, there's 2 stages to this problem. There's this first 3 seconds where I was pushing the box, and then there's also going to be stage 2 from the momentum the box had up until it stops because of friction. Okay? The friction is going to make the box stop. So the first thing I'm going to do is I'm going to calculate the distance that this object moved in the first 3 seconds, right? Because I'm busy with the problem. I've got all the information in front of me. So let me quickly calculate that. Right? So I want to find displacement, and I'd like to find it based on the solid information that I have. So I'm going to use v squared is equal to u squared plus 2as. I don't want to sorry, I'm using the wrong formula. ut plus a half at squared. My apologies. I don't want to rely on my velocity because it might be wrong. So I'd rather rely on the information that I've worked out previously. So from here, we can just plug in what we have. That's going to be 0 because the initial velocity was 0. And so the only thing we have is this half times the acceleration of 0.5 and times the time, which was 3 seconds squared. On my calculator, we have 9 times 0.5 times by 0.5, which is 9/4, which is 2.25. So we have 2.25 meters. Okay. That is for displacement 1. Okay, so that's how far the box moved while I was actually applying this force of 50 newtons. Right, after 3 seconds, I stopped applying the force. So now everything's changed, right? I need to redraw my diagram, right? I don't actually have to redraw very much. All I need to do is remember that now this force over here is gone. Right? There is no more force in that direction. I've stopped pushing the box. But the process is going to be exactly the same, right? Just for completion, I'm going to redo it, but you can actually use your work from the previous one, right? I'm going to resolve vertically to find the normal contact force, right? This is perpendicular to the direction of motion, so it's in equilibrium. Now that I have my normal contact force, I'm going to find my friction force, right? The coefficient of friction is the same, 0.45 times by 100 equals 45 newtons. I know it's simple, silly that we're redoing it again, but if it helps you to solve the problems, then resolve everything again. So I can update my diagram. There's my 45 newtons. And remember, it's acting against the direction of motion. My direction of motion is still in the same direction. That hasn't changed. Right, now I can calculate my new, it's actually not going to be acceleration. I stopped pushing the box. It's going to slow down, which means it's going to decelerate, okay? right? This is my net force again. So my net force is the net force in the direction of motion. That's going to be the horizontal forces, right? The 45 newtons friction is going against the direction of motion. So it's negative 45, right? Not positive 45. Right? And I don't have any other forces this time. There is no pushing force in the direction of motion. The mass of the object is still 10 kilograms, and the acceleration is what I'm trying to calculate. That's going to give me an acceleration of minus 4.5 meters per second. Right, and now identical to the first problem, I'm going to state all the information that I have. So what do I have? What information do I have? Well, I know the initial velocity, right? Because when I stopped pushing the box, the velocity was 1.5 meters per second, right? That's kind of what I calculated in the previous one. Sorry, that's not v squared, that's u. I also know the final velocity. The final velocity is going to be 0 because that's what the velocity is when something stops. And I've just calculated the acceleration as minus 4.5 meters per second. So when we have these two-stage problems, remember the final velocity from stage 1 is the initial velocity from stage 2, right? Because they are flowing one after each other. Right, in order to calculate the displacement in one go, we'll use this formula, right? Because it uses all the information that we have. And so substituting in, I'll get 0 is equal to 1.5 squared plus 2 times minus 4.5 displacement. And if I quickly punch that into the calculator, it's 1.5 squared divided by minus 4.5 times 2, which is 9. That's going to give me a quarter, 0.25 meters, right? Very importantly, that's for stage 2, okay? So I want to find the total distance the box has moved. So I can say that the total distance is equal to the displacement after stage 1 plus the displacement after stage 2, which is equal to 2.25 plus 0.25, and that's going to give me 2.5 meters. Everybody happy with that? You see how we can do things in stages, right? Yep. Especially with friction, all right? Because remember, friction always acts against the direction of motion, which is going to become very evident in the next problem. Okay, here we go. We have a ball, okay? And it's 3 kilograms. So I'm going to start putting the information into my diagram. So my weight is 3 g newtons, right? Remember, vertically, even though there is a slope in question. Okay. The slope is at an angle of 20 degrees. There's my 20-degree slope. And the coefficient of friction is 0.3. So I can highlight that because I know I'm going to need that at some point. So part A says find the distance up the slope when the ball comes to rest. Okay. So I'm setting my direction of motion up the slope so that I can solve parallel to it in order to simplify things. Okay? Unfortunately, that means I need to take the component forces of my weight force, right? Because they are not, it's not parallel or perpendicular to any of the other forces. From here, the process is going to be exactly the same as before. So we need to resolve vertically, right? We need to resolve vertically because we need to find the normal contact force, okay? Because we don't know the friction force, and we need to know the normal contact force in order to calculate the friction force. So resolving vertically, I have I have the normal contact force going in one direction, and I have the vertical component of that weight force going in the opposite direction. That's going to be 30, it's the adjacent side cos 20 degrees. So there's my vertical one, resolved vertically. And like before, next step is now friction force. Right? So do I have the coefficient of friction? Yes, it's 0.3 multiplied by the resultant force, right, which is 30 cos 20, right? And I'm even going to take 30 multiplied by 0.3, and I'm going to get 9. Try to keep your trig, you can if you want, keep your trig identities together until the end. Then you don't have to try and remember which number you stored it in or which letter you stored it in on your calculator. Okay. Right, now I have my friction force, okay? I have no force going up the hill, right? This ball was rolled up the hill with an initial speed, but the moment it left the person who threw the ball, it had no more pushing force. Okay? And so what we can do is we can calculate the net force, right, which we know is going to be negative, which makes sense, which is going to give me a deceleration. Okay? Remember, this object is decelerating. It's not accelerating up the hill because we've stopped applying a pushing force. So to find this, right, I need to resolve horizontally. Well, actually not resolve horizontally. We can't resolve because they're not in equilibrium. There's a net force going on here. So we can actually use our net force equation, right? Newton's second law. So on our diagram, we can go and look which forces are acting against the ball. Well, we have the friction force, and we also have this little horizontal force also from the weight, right? The horizontal component there, right? They're both acting against the direction of motion, the other direction. So I'm going to have minus 9 cos 20 minus, right, that's going to be 30 sine 20. That's that little horizontal component there, right? And that must be equal to mass times acceleration. The mass of the object is, whoops, 3 kilograms, and the acceleration is the thing that I'm trying to find out. It's just now a simple process of punching everything into the calculator. So we have minus 9 cos 20 minus 30 sine 20, and we need to divide that by 3. That's going to give us an acceleration, or actually a deceleration, of minus 6.23927, etc., which we can simplify to minus 6.24 meters per second squared. And I'm immediately going to store that into my calculator. Okay? Because I want the exact answer. Right, now that we have the acceleration, we can go back and read the question. It says we want to find the distance up the slope, all right? So let's think about the information that we know. We know the initial velocity is equal to 10 meters per second, right, in the direction of motion. We know the final velocity is going to be 0 because the distance it travels up the hill, its maximum distance will be up until the ball comes to rest. Okay? And we've just calculated the acceleration as minus 6.24 meters per second. So you, I guess, can start getting used to the fact that you're going to be using that guy quite often. I'm just going to move this out the way. Minus 6.24, and displacement is what we're after. Okay, now you have your, you should still have your acceleration in your calculator. And so what you can do is you can multiply it by 2, because it's 2as, right? You can multiply it by 2, and you can logically in your head hopefully work out what 10 squared is. So you can take 100 divided by, push the answer button on your calculator, and that should give you a displacement of 8.0137 blah blah blah, which we can round to 3 significant places of 8.01 meters. Okay. And I'm going to store that in my calculator as well. Okay. So I have that in my calculator because you can see this is a multi-part question. I know I'm going to need it just now. Okay, now we're going to get to the second part. Right? Now things are going to change. So they want us to show that after the ball comes to rest, that it starts rolling down the slope. So in other words, what we need to prove is that there is a force in the direction down the slope when the ball comes to rest. Do we need to change our diagram in order to do that? Do we need to change anything on our diagram to prove that? Right, I want you to think about the ball on the hill now. It's come to rest. In which direction is friction going to be acting now, Dominic? Is it still going to be acting in the same direction? The friction force. Is the friction preventing the ball from going up the hill now or from rolling down the hill?
Now the friction is preventing it from rolling down the hill.
So the friction force has changed, which means that we need to change our perspective, right? So we're going to quickly, right? It would be nice for you if you could do this, hey?
Yep, copy, paste, there we go, all sorted.
All sorted. We can just solve. Let's get rid of, and you can just tap, tap, tap. See, it's all gone. Tap, tap, tap. Right? We need to tap, tap, tap this guy to the other direction, right? Because he's now not going in the. I'll just put him. So our friction force is now going in that direction. So what we want to do is we want to prove that the force going down the hill is greater than the force going up the hill. In other words, that the friction force is less than that little horizontal component, right? And so we just need to resolve for all the forces again to do that. So we're going to resolve vertically. And it's going to be exactly the same as before. R is going to be equal to 30 cos 20. Right, that can work out the friction force. And it's going to be the same because it's the same coefficient. So 0.3 times 30 cos 20. That's going to give me 9 cos 20. So this is my friction force here, 9 cos 20. I need to compare that to the force going down the hill. So what's the force going down the hill? Right, the force going down the hill is that 30 sine 20. Right, I'm going to change my direction of motion, right? I'm going to assume that the ball is going to roll down the hill. I could be wrong, but I'm going to, with a little bit of thought here, I'm going to say, I think the ball is going to roll down the hill. So I'm going to change my direction of motion. Right? I'm going to say the direction of motion is going to go down. Remember, when I change the direction of motion, I need to remember that now things down the hill are positive and things up the hill are now negative. Right? Negative just means in the opposite direction of what I've called the direction of motion. So here we go. Let's see what the net force is. Right, I'm going to subtract that friction force because it's going in the opposite direction. And let's see what we get. Now remember, if I get a positive number, that means the direction of motion, or the ball is going down the hill in the direction of motion. If I don't get a positive answer, then I've made the wrong assumption. I need to remember and realize that. Right. What I end up with is a positive force. Right. So I can prove, what have I done? I've got 1.8033 something, something, something. In other words, there's a positive force, meaning that the net force is going in that direction. Okay. Alternatively, I can also now calculate the acceleration. Remember, force is equal to mass times acceleration. If I can prove the acceleration is positive in the direction of motion, I can also prove that this ball is rolling down the hill. Okay? I've calculated the net force already, so that's pretty easy. The mass of the object is 3, and we want to calculate the acceleration. So I'm just going to divide the answer on my calculator by 3, and I'll get an acceleration of 0.6011, blah, blah, blah. Right. Because I've proved I have a positive acceleration, remember, I've now changed acceleration also down the direction of motion. Because I've proved that it's positive, that means that the ball must be rolling down the hill. If you didn't change your direction of motion, that's fine. Except now you would be expecting negative answers because the ball would be going in the opposite direction to what you called positive. Remember, we can change the direction of motion if we want, right? To make it more convenient for ourselves. We just need to remember what a negative number means to us when we get them. Right, the final thing in the question says, find the speed of the ball when it returns to its starting point, okay? Well, its starting point, that's where we need to remember from its starting point up to where it got to the top of the hill, that's how far it moved. So we need to use that in solving, okay? So let's think about everything that we know about this ball. We know the initial velocity is 0. It started from rest. We know the acceleration is 0.601 meters per second, and its displacement, well, to get back to its starting point, it needs to travel 8.01 meters. I want to find final velocity, so final velocity is v squared. And so I can just solve. Right, that's going to be 0 plus 2 times 0.601 times 8.01. This is where having these things stored in your calculator is very useful. Okay, I have my acceleration still plugged into my calculator, so I'm going to multiply by 2, and then I'm going to multiply by my displacement, which I saved in my calculator. What I suggest you do is, if you do that in the exam in pencil, just write the letter next to the answer if you're going to forget which letter it was. Okay. That's going to give me v squared of 9.634, but I'm not actually interested in that. I'm more interested in what the actual answer is. So I'll take the square root of that. Remember, we get a positive or a negative number, but we want the positive number because it's going in the direction of motion. Right? And so I get 3.10 meters per second. Hopefully that wasn't too much of a mouthful for you guys.